So far, we've introduced the eigenvalue problem, and we've shown how to solve it mathematically. Now let's look at a couple of applications. And this first application, let's look at how to solve a system of coupled ODEs. So, so this is a system of coupled ordinary differential equations. And those so that the first equation is x prime is equal to x plus 4y, and y prime is equal to x plus y. And here so x prime is equal to some derivative of x plus some independent variable, for example, t. And likewise, y prime is equal to the derivative of y with respect to the independent parameter t. Okay, so you should notice that the ODEs are linear. They're each term is proportional to x or y or its derivatives, and the coefficients are constant. And they're homogeneous. There's no part in either equation that's not a function of x or a function of y. So therefore, we know that x of t is proportional to e to the rt. And let's call the constant of proportionality q1, for example. And likewise, y of t is proportional to e to the rt, where q2 is the constant associated with y. So if we use the form of these, assume this form of the equation, and substitute back into the initial form, we get on the left-hand side of the first equation rq1, and that's equal to q1 plus 4q2, and that's all multiplied, of course, by e to the rt. So this is our first equation. And then the second ODE becomes RQ2 is equal to Q1 plus Q2, again multiplied by e to the RT. So again, we've just substituted these expressions in for x and y into this equation, and we have these two coupled equations. And if we cancel out the e to the RT, we can write this system of equations as a matrix equation of 1, 4 times Q1 and Q2 being equal to R times Q1. So this is the first equation. And then for the second equation, we have a 1 and a 1. So Q1 plus Q2 is equal to R times Q2. Or, in other words, this is A Q is equal to R Q. And R is a scalar quantity, so this is an eigenvalue equation. This is the eigenvalue equation. In other words, when we multiply A by Q, it doesn't change its direction, it only changes its length by this factor R. So step 1, again, is to solve for the eigenvalues, which in this case we're calling R. And we do that by taking the determinant of A minus IR and set that equal to 0. And when we do that, we have, in this case, we'll have a second order polynomial, and we'll get the eigenvalues of R1 is equal to 3 and R2 is equal to -1. The second step is to solve for the eigenvectors for each eigenvalue, for each R. And we find that for R1 is equal to 3, we get the eigenvector of EI is equal to alpha, that's our free parameter, times the vector 2 and 1. And for R2 is equal to -1, we get the eigenvector E2 is equal to beta, our free parameter, times the vector -2 over 1. And recall that these gave us our coefficients for each value of R. So the solution becomes X and Y is equal to Q1 over Q2 for the first eigenvalue, and that's alpha times 2 over 1 e to the 3t, that was our first eigenvalue, and then we have Q1 and Q2 for our second eigenvalue, which is -2 and 1 e to the minus t power. And just so that's what the solution is in matrix form. Writing it out in equation form, we get x equals 2 alpha e to the 3t minus 2 beta e to the minus t. And y is equal to alpha e to the 3t plus beta e to the minus t. And that is our full solution for x and y in our system of coupled equations. So that was our first example of solving a system of coupled ODEs. Now let's look at the second example of a Markov process. And a Markov process describes the state of a system. Basically, it says that the state of a system at a point in space or time equals some function of the prior state of the system. So this is a general description of a Markov process. And we could write this mathematically, for example, as x at some state n plus 1 is equal to our function of x at the prior state, prior in position or in time. And the example here is an example of population dynamics. So we have a population. We'll change our variable to variable p, n plus 1. We have a population at a certain time being controlled by the population, again, P at the previous time. So let's describe P as equal to X, Y, and Z, where X is the population of Delaware, the number of people in Delaware. Y is the population of Maryland, Delaware is abbreviated DE, and Z is the population of Pennsylvania. And so I'm going to draw a diagram that shows how the populations change between the three states. So here we have the population of Pennsylvania. So this again is Z. And we have the population of Maryland, which is Y, and the population of Delaware, which is X. And the story goes that each year, 8% of the population of Delaware move to Pennsylvania. And I'm going to write a subscript N to describe the previous state for each of these. And in a given year, 10% of Pennsylvanians move to Delaware. From Delaware to Maryland, 20% of people living in Delaware in 1 year move to Maryland, and 12% of people living in Maryland move to Delaware. And then finally, the interaction between Pennsylvania and Maryland is that, what is it, 0.3% of people from Pennsylvania move to Maryland, and 10% of people from Maryland move to Pennsylvania. And so, so the assumption here is the populations change only by people moving between states. That is, the birth and death rate balance out. So birth and deaths don't change the population. So we can now write the population of Delaware in the next year, the n+1 year, as equal to the starting population in the year before minus the percentage that leaves Delaware. So that's 0.2 plus 0.08. And then we also have to add the amount that comes, the 12% that comes from Maryland, and the 10% that comes from Pennsylvania to describe the change or the new population in Maryland. We have its starting population the year before minus the percentage that leave Maryland, and that's 12% and then 10%, plus the percentage of Delaware that enters it, plus the number from Pennsylvania that enters Maryland. So that's 0.03 ZN. And finally, the number of people in the next year in Pennsylvania is equal to the previous population minus the 0.03 plus 10% that leave it plus the 8% from Delaware that enter Pennsylvania. 8%, not 80%. Plus the 10% from Maryland that enter Pennsylvania. So here's our system of coupled equations showing the Markov process of the change in population due to movement between the three states. So we can write that as the populations in the next year being a matrix multiplication with these elements times the starting populations in the previous years. And this describes the population again in the next year being a matrix multiplication with the population in the previous year. Okay, so this is a Markov process showing how the populations change for each year, but it's not an eigenvalue equation because we have two different vectors on either side. The question we'll now ask, is there a population distribution P such that, or I should say, is there a population P that never changes? That is there an equilibrium population state? In other words, if we let people move to and from the state, will there ever be a point where the populations in each of the states doesn't change? And to answer that question, we would want to solve the equation AP, which is that steady state population, is equal to lambda times P, in this case where lambda is equal to 1. So this states that from each year, even though people move, the populations in the states are preserved. And this is an eigenvalue problem. And we can ask what that steady state population is. If we in fact find that there is an eigenvalue equal to 1. So first we have to solve for the eigenvalues of P, I should say, sorry, not P, of A. And if 1 equals 1, then the answer to the question above is yes. And in fact, there is for this particular example, lambda 1 indeed is equal to 1, and the eigenvector associated with that eigenvalue is equal to a free parameter alpha times minus 0.56 minus 0.62 and minus 0.82. So the solution given, as you can see, all shows negative populations. But you know that alpha can be anything. So the physically reasonable solution is one which shows positive numbers. And the essential information is the relative sizes of these numbers. And so again, this gives the steady state or equilibrium population after many years of this Markov process occurring. So if as n gets really big, eventually all the movement between the states will continue to occur, and the final populations, the steady populations, in a relative sense, is given by this vector 0.56, 0.62, and 0.82. So that was our second example of the application of the eigenvalue problem. And in that case, this was the Markov process of population dynamics.